Thank you, Eugene. Okay, so on the right-hand side, we have what we may typically recognize as quadratic equations. And on the left-hand side, we have something called equations that are quadratic in form. So I want you to just take a minute or so, look over the left side and the right side, and see if you notice any patterns at all. Maybe even why would we call the things in the left-hand column, these equations, quadratic in form? So just take a look, see what you think, discuss it if you want, or just write out what you think right underneath, and we'll talk about it in a minute or two. Okay, so let's just see if we noticed anything, or you noticed anything, and then we'll talk about the left-hand column and the right-hand column. Anybody want to discuss what they noticed? There's like no one answer here. There's no right or wrong answer, really. Well, there's some right answers, but I mean, really, whatever you notice is probably going to be true. Whether it helps us or not will determine whether it does. So anybody want to say or recognize, did you recognize any patterns at all in the right side and the left side? That the both polynomial equations, yep. Quadratic equations are polynomial equations, and all of the things on, well, this one is not a polynomial equations because we have rational exponents. Polynomial equations will always have whole numbers up here, okay? So if they're what? Right, so like this would be an equation that we could either call, we would just say this is an equation with rational exponents. Yeah. So polynomials are defined so that all the exponents you see are like 0, 1, 2, 3, 4, 5. Okay. So any other patterns that you notice between the two columns? Anything at all? I heard some talking going on. They all equal 0, right? They're put in standard form. Yeah. What were you guys discussing on table 2? Yeah. Okay, so you've noted, so basically all I did was take the equations on the right-hand side and exactly the same A, B, and C values. But let me just give you one that wouldn't be where this pattern, whatever I'm trying to get you to see, would not hold. So if I took this equation and I did something like this, this would not fall in the category quadratic in form. So there's something going on that you see always happening on this side that doesn't have to do with the A, B, and C. That's exactly being replicated on this side. Could you factor this first equation over here on the right-hand side? Could you factor this? You could. What would it look like if you factored it? Go ahead, Di. Okay, factors of 9 that add up to 10. What are the factors of 9 that add up to 10? Not 1 and 9. Okay? So that could be factored, okay? Can we factor this one? What's the only difference between these two? What's the only difference? The power of x, right? So this first one is x squared minus 1 times x squared minus 9. So the only difference is this equation has a power that's 2 times bigger than this power, right? The 4th degree versus the 2nd degree. So when you look at its factors, instead of each factor being little baby linear factors to the first power, they're both quadratic factors. Okay, that's one thing. So we could solve this equation just by factoring it. Okay, and you're just not used to doing a lot of things unless they look exactly like they did under the quadratic equations. But there's something else about these equations that allow you to factor them like this. And it doesn't look like, at least nobody has volunteered the pattern. So I guess I'm gonna have to like burst the bubble and tell you. What, Coleman?
I get it, I can't explain it.
Well, what do you get?
I mean, I agree, the pattern you're pointing out, it's like x value, instead of having a given x value, you have it replaced by another quantity.
Right.
So like instead of the second one there, x plus 3 is instead of x. Like
Yeah.
X plus 3 in that case.
Okay, so let's suppose we just replace x with a x plus 3 with a smiley face.
Yeah.
All right? Then it looks almost exactly the same as the right-hand side.
Yeah.
But there's something else that's going on that doesn't occur here. This can't go over into this column because it's missing a pattern that these all have in common. Yeah. Yeah. This is not ax squared.
The first unit is always the first unit is always the middle unit squared.
Okay. The first unit, what does he mean by unit?
Middle variable squared.
Right. What does he mean by unit when he says unit? I know what he's thinking of. But what do we call these pieces here when we have this? It's really important if we're going to be in a math class that it's like you wouldn't go to Spanish and speak French, right? We don't want to go to math class and speak English, right? So what do we call those pieces? They're not units, okay? Terms. So what Coleman's trying to say is he notices that the first term is the power is always twice the middle term. So that's the pattern. Look at the right side. This is a 2. What's the power for the middle term here? 1, right? So you can either say the middle term, the power of the middle term is half of the first term, or the first term's power is twice the middle term. Okay? Notice the same pattern over here. Because when you multiply these binomials, the middle term has to have the power that's half of your leading power here. Notice what it is here. This is a 2, this is a 1. What about this one right here? Is this first term is 2/3 twice as big as 1/3? So that's the pattern that's going to say to you, these can be put into a form that looks quadratic, because quadratic equations always have that pattern that the power of your first term is twice the power of your second. And then you have a constant here. The last term is a constant. So notice once you recognize that, then you can just approach it like you would approach any quadratic. You could factor it. Sometimes it looks a little funky to you because you're not used to seeing things here like 2/3 and 1/3. But let's take a look at this middle one, right? This last one right here. Once you get the idea that these are quadratic sort of in form, and you say, oh, this is one of the ones where my first power is twice as big as that one, then it's just a question of factoring it, if you can factor it. So here, if this looked just like this, you'd have the same problem if you were trying to factor this one, because a lot of you have trouble factoring when there's a number other than 1 here. And hopefully you took some time back in section P4 or P5 to do some factoring, but this would be 5x plus 1 times x plus 2. That's how we would factor that one. So the only difference here is instead of it being x, notice x is to the first power. It's the same as the power on our middle term. So this is going to be 5x to the 1/3 plus 1 times x to the 1/3 plus 2. And if you use the distributive property twice, which you call FOIL, 5x to the 1/3 times x to the 1/3, if you multiply those two out and use your exponent properties, when you multiply, you add exponents, you're right back to 2/3, which is what you started out with. Your middle term is 1x cubed, x to the 1/3. And your last term there, your outer term is 10x to the 1/3. And you can combine those to get you 11x to the 1/3. And then finally, you have your plus 2. So sort of what got you through quadratics, one of your strategies was to factor. Okay. So that's one of the things you want to look for. So if on next Monday's test, you see an equation where the power of your first term is twice as big as your second term, your middle term, and then you have a constant, in your mind, you could make it look really nice, like the ones in column, the right-hand column, and say, oh yeah, that's just like a quadratic equation. I can just factor it. However, we haven't solved our problem here. Notice these two factors are set equal to 0. So to finish this off, you would have to set each factor equal to 0 and solve. And that's why we learned how to do equations the other day that had rational exponents. So we could solve equations like this. Okay? So how would we proceed with these two equations to solve these two? What would you do? Subtract 1. So we're working on the first one, we would subtract 1 from each side, and we'd get 5x to the 1/3 equals -1. Then divide by 5. Both sides, we would divide by 5. That's right. And that would give me x to the 1/3 equals a -1/5. And now we have to undo. You could either, some of you may prefer to call this the cubed root and use your radical symbol, the cubed root of x, or we can use what we did the other day. We can raise both sides to a power that when we multiply 1/3 by this power, we'll get x to the first. And what was that magical number that would do that? The reciprocal, right. 1/3 times 3 is always going to give you 1 when you multiply it. So we get x to the first equals -1/5 to the third power, which is -1 over 125. So that's one of your solutions, -1 over 125. So it's just applying what we did the other day to each of the factors because they're both rational exponents. Okay, so let's take a look at this. Why don't you try at your seats to come up? Let's solve. Why don't you all solve this one for x, following the same pattern we just did with the first factor. You try that at your seats. If you have any questions, just put up your flag. Okay. Anybody got an answer for this? X to the 1/3 plus 2 equals 0. Any answers? Yeah, here. You got 8, yeah? You got -8. Oh, that's okay. So let's take a look. We're sort of in the ballpark. It's going to either be 8 or -8. Let's see what we get. We subtract 2 from both sides. Everybody agree with that so far? Now we cube both sides and we get x equals -2 cubed. So when we have a negative base and an odd exponent, we stay negative. Okay, Karen? All right. Any questions on that? Okay. So you will see on your lecture notes, you will see all this stuff called use substitution to solve this equation. And I just wanted to point out that if you get something like this, I just want to show you another way to approach it. You can factor this just like we saw a minute ago. You don't have to be all wigged out because you see u to the x to the 4th there. This is not, you don't use the same method we used on Monday because if you had x's all the way across here, like if this said x to the 4th minus 10x squared plus 9x, then this wouldn't be quadratic in form. It has to have a constant here. If we had an x instead, 9x instead of 9, then you would pull out a common factor first. We don't have that here. So one choice instead of doing what I've laid out for you here, is to just simply factor each of these. And notice each factor, when you set it equal to 0, is just the difference between two beautiful perfect squares. And so if you factored this, you'd get x plus 3 times x minus 3 equals 0. And if you factored the second one, you'd get x plus 1 times x minus 1 equals 0. So you'd have 4 answers here. Notice your degree is 4 as well. So that's a little hint sometimes. Oh, maybe I should be looking for 4 different answers. Sometimes you may not get 4. We've seen situations with that. Sometimes you get 4 or less. But 4 is the most you can get. So your solution set here would look like this: -3, comma, -1, comma, 1, comma, and 3. That would be your solution set. So that's one approach. The book is having you try to like reframe the equation, like see it differently. Because if you saw this equation as some number squared minus 10, some variable squared minus 10 times that variable plus 9, you'd say, oh, I would just factor it. It's a quadratic. So what they do is they have you substitute with just any baby letter. So it's called U substitution. This is, they use the letter U a lot when they substitute back in. And this is a common strategy. You'll see this a lot in, say, calculus, for those of you going to calculus, this idea of U substitution. So basically they say, I don't like seeing things x to the 4th minus 10x squared plus 9. I really would like it to say something squared. So basically you say, what do I square to get x to the 4th? And that is x squared. So wherever you see x squared, you're going to replace it with u. So notice my first term here can be written as x squared squared. So that's going to be the same as u squared. So you're just letting x squared be the number u, the variable u. I keep saying number, sorry. So this now looks like this. When I substitute x squared, which equals u, into this equation, this now looks like an equation you can solve. And guess what? We just solved this a minute ago. Now you would solve it as you normally would factor a quadratic. You would do this. You would set each factor equal to 0, just like we have always done. And now the only difference is you have to solve this for u. So you could do u equals 9, u equals 1. But now you say my original equation wasn't written in terms of u, it was written in terms of an x. So now you replace u with what you substituted it for, which was x squared. Replace this with x squared. And now you can factor this by subtracting 9 and 1 from both sides, or you can try to remember the square root property, which tells you have two answers when you take the square root of both sides. Okay. So this u substitution is not necessary. It just helps you see a way of solving it, because it looks like you're more familiar with this type, u squared minus 10u plus 9, than you are with the other. But it's just really a training exercise for you. If you can feel comfortable here saying, I can factor this just like I factored all the other quadratic equations, then you don't have to do this substitution. It really just depends on how you see it, how you recognize it. So let's take a look at the next one. And again, this one looks really funky, right? When you see this, you go, the first thing, I know the first thing you're going to want to do when you see something like that. And it will make, you'll get to the same answer, but it will make life a little more work. You'll have a little more work. Again, the pattern here is so critical. See, 2, half of 2 is 1, and then you have a constant. That tells you this can look like a quadratic equation. So the thing here is not to do this. You can. What if you were left to your own devices, if I just said solve this equation, what would you do? If you didn't know about u substitution, what would you do? Yeah, you would, go ahead, Joe. right? You would square out x plus 3, right? Right? You would do all that, right? And that's perfectly fine. It's legitimate. You're not doing anything incorrect. So if you do all this, it would look like this. When I square x plus 3, I get that. And then I'm going to distribute my 7 through, and I'd get this. Okay, no big deal. And then I'd combine all my like terms. I'd get this, and make sure I don't make any mistakes. Keep your eye on me now. Is that right so far? Okay. And now, what do you have? Quadratic equation, factors of 12 that add up to 13, no problem. X plus 12, x plus 1 is 0, and you'd have negative 12 and negative 1 for your solution set. Then you'd have to go back and check to make sure they both work. Okay? Just another approach is to use this U substitution, because we get a little weirded out when we see these things, to just say, let U take the place of the base here, which is x plus 3. So everywhere you see an x plus 3, you just replace it with a little baby U. So now it looks like this. So all I did is say, wherever I see an x plus 3, I'm just going to make it this single letter U, which makes me feel a little more at ease. And then you factor this. Factors of 18 that differ by 7. What are the factors of 18 that differ by 7? 9 and 2. Which one of those numbers gets the plus sign and which one gets the minus? The 9, because you ended up with plus in the middle. And you got a U and a U. You set each factor equal to 0. It's the same old story for the same old game. You solve U equals negative 9, U equals 2, but your original equation wasn't in terms of U, it was in terms of x. So now you say, what did I let U equal? Oh yeah, I let U equal x plus 3. So then you replace U with what it was equal to. And then you have a little baby linear equation to solve, and you get x equals negative 12 and x equals negative 1. Okay, so that's two different approaches to exactly the same type of problem. You could, on your own, do what you might intuitively do, which is to square everything out here. As long as you square x plus 3, okay, you'll be fine, right? But if you call this x squared plus 9, you're going to be in trouble, right? So you just got to remember how to square these binomials. Hopefully by the time you leave this class, no one will say x squared plus 9, right? Or you can use this idea of U substitution. It's not critical. It's just sometimes helpful for seeing how to approach it. Right. Any questions on either of these? Yeah, Andre? Sure. Any questions? Okay, so again, you'll have, so this is the kind of thing like on this study aid guide I gave you. This type of equation comes down here where it says quadratic in form. Do I even have that on here? Ooh, I don't have it on here. We forgot it. So you could add another little row at the bottom of the study aid that says quadratic in form, and put one of these types of equations in there with your own idea of how to solve it. What works for you? Okay, so you have to add another little row to this, quadratic in form. Yeah, I'll fix that for next semester. All right, so we've already done this one. We've done this one. Unfortunately, I did it for you. You can read through all the steps if you want. But let's take a look at equations involving the absolute value. So let's use our graphing calculator to solve this equation. I think we can probably figure out what the solutions are without any kind of calculator, but I want you to see it. So here's our equation. Absolute value of x equals 3. So we're going to use the idea of taking the left-hand side and putting it in for y1, and the right-hand side and putting it in for y2. And we're going to see where they what? Intersect. Okay, so let's take a look at where they intersect. So let's do that. And oops. If you have a calculator, great. If not, we'll just copy out the screen here. All right, so y1 equals absolute value. Where do I get the absolute value? That's in my math button right here. And I go over to NUM, and there's absolute value right there, ABS. So I hit enter, and I put an X in, close the parenthesis, and then I just get rid of everything else that's there. All right. Then the right-hand side of my equation is 3. So I just put in a 3. So this is just going to be a horizontal line straight through y equals 3. And this is going to be my absolute value that looks like a V. So I think my standard window will be fine here. So we're just going to say zoom 6. There's our absolute value of x. There's y equals 3. And where are they going to intersect? Where will these two intersect? Well, we know the y values for everything on this horizontal line. Every single y value is 3. So what are the intersection points going to be right here? 3 and negative 3. Well, how'd that happen? Ooh, ow, what did I get? Oh, how do I get rid? Oh, whew. I haven't even seen that symbol before. Hey, what happened to my graph? All right, let's go back to my, technology is wonderful, except for when you screw up, right? Let's see. I want to get rid of this whole window. Cut. There we go. All right, so let's go back to my graphing calculator. All right, so there's what I want to copy. We could go to the intersection button and get the answers, but I think we can clearly see the answers here, a 3 and negative 3. So if I asked what the solutions are to this equation here, I'm trying to get back over to the left here, and oh, there we go. So let me make this a little bit bigger for you to see. You can just put a quick copy of this right at your seats. So we can see here that if we were to label each of these graphs, we would call this y equals the absolute value of x. That would be the V shape. And this horizontal line, that's y1. And the horizontal line is y2 equals 3. And where they intersect are at negative 3 comma 3 and positive 3 comma 3. Notice the y values are both 3 because they lie on this horizontal line. And this says when I take the absolute value of negative 3, I get 3. And when I take the absolute value of 3, I get 3. So those are the 2 points. So the solutions are the x values. The solutions are the x values. So the x coordinates of these two solutions are negative 3 and positive 3. So that tells us that we have 2 numbers that are solutions to this equation. When you have an absolute value equation like this, you will always have 2 answers because x can be a positive 3 and x can be a negative 3. Okay? So how do we solve absolute value equations? Well, basically what you do is you take all the stuff that's on the inside of the absolute value, all the stuff. That's what I call it, stuff. You want to solve it so that you get your absolute value all by itself on the left side or the right with some stuff in the middle, and you have a constant over here. That's what you want. And then you say, all that stuff on the inside could either equal that constant, just like x could equal 3, or x could be the opposite of 3. So the stuff could equal the constant, or the stuff could be the opposite of the constant. So basically, they're not going to write that in a math book stuff. What they do is they represent it like this. They say if C is a positive real number, and U represents any algebraic expression, it could be simple like x, or it could be x plus 10, it could be 2x minus 5. That's what I call the stuff. U is some algebraic expression inside an absolute value. And when it equals a constant, then we know that U is either equal to C or it's equal to its opposite. And that's how you approach every single absolute value equation. So let's work through each of these steps for this absolute value equation. First thing you notice is there's a 1 in front of this absolute value. It has a coefficient of 1. There's nothing hanging on the outside. There's nothing being added or subtracted. So we don't have any work to do to this to isolate the absolute value. It's already there on the left side. So One of the problems that students have when they see something like this is they treat the absolute value like it's a parenthesis and they start subtracting 1 from both sides. You can't take anything out of there like it's parentheses. All you can say is whatever this is inside, the only thing 2x plus 1 can be inside that absolute value is either the number 11, because the absolute value of 11 is 11, or what else can that stuff inside there be? Negative 11. That's all it has the choices to be. Nothing else in the world. So this stuff, what we call 2x plus 1, can either be 11 or 2x plus 1 could be a negative 11. Because I know the absolute value of 11 is 11 and the absolute value of negative 11 is 11. So whenever you have an absolute value equation, you must rewrite it without the absolute value as 2 equations. One is the oops, thank you. Yell at me when I put a 1 in instead of 11. Okay, so one of them just says, hey, if I'm 11, I'm cool. You solve this, there's no problem. You get x equals 5. I'm not going to go through that. You can solve that easily. You go back and check. 2 times 5 is 10 plus 1, 11. Cool. This is going to be x equals negative 6 when you solve that. Go back. 2 times negative 6 is negative 12 plus 1 is negative 11. Absolute value of negative 11 is 11. So absolute value equations are not too difficult to solve as long as you remember that you have to set up 2 equations in order to solve them. Okay? Because there's 2 values that we can put inside here to have this be true. Any questions on this? Anything at all, either in understanding how we did it or how to get the solution? All right, so I want you to try this one at your seats. It's got a few more steps. So what did we get for the solution set for this? If I were to write it as a solution set, what did you get? Negative 3, comma 4. Okay? And people are asking me if this is correct. How can you answer that question for yourself? You plug it back in where? The original, always to the original equation. So if you go back to your original equation and you plug in a negative 3, you can check this for yourself. You don't need me and you don't need the answers, right? So you just say 3 times, this gives you a negative 6. Take away 1 plus 4 equals 25. Notice what that gives you inside. A negative 7. The absolute value of a negative 7 is 7. So this gives me 3 times 7 plus 4 is 25. 21 plus 4 equals 25. If you go back and substitute a 4 in, you'll get 8 minus 1 is 7. You'll get exactly the same answer. Okay. So what did you all come up with in terms of why number 8 has no solution? Why the solution set for this is the empty set? Why is this the empty set? What is C here? Not yet, because when we've solved for C, it's negative 2. So when you solve this equation, you start by subtracting 4 from both sides, and you get the absolute value of x equals negative 2. And we know that there's no number in our system that we can put in here and take its absolute value and get a negative number. So this is why this has no solution. So if I gave you something like this on your test Monday, and I asked you if this were true or false, you could say false. How could you change the sentence so it would be true, or how could you show a counterexample? There's a really easy way to change a sentence. You could make it x minus 4, and that would be okay, because when you add 4 to both sides, okay, you get you get a positive number. What else could you, a real simple thing? Yeah, just go like that. Doesn't equal 2. And then you don't have any muss or fuss, right? See, those 2 things aren't equal. It's false. So you don't have to do too much brain power there to change the sentence, right? Use too much brain power. Okay, the final thing we've got to cover is solving linear equations, linear inequalities. And to do that, we're going to introduce a new notation for representing a solution set. And that new notation you're going to be using for the entire rest of the course, and it's not as bulky as your set builder notation, which we learned on like the second day of class. So if I asked you to represent the solution to this linear inequality, all the work has been done for you. So here's my linear inequality. X is less than or equal to 7. And I asked you to represent it with a number line. How would you represent that? Does anybody remember how you did it a long time ago? How would you represent X is less than 7 on the number line, real number line? A filled in circle where, Matt? At 7. And why? All right, and then you would just do an arrow continuing to the left, and where does it stop? Doesn't. Right. Doesn't stop, and we say that that arrow goes towards negative infinity. Okay, which isn't a number, it's a concept. All right, so why did I do a solid dot? Why is this solid? Right, because of that little equal to 7. X, to make that inequality true, I could put any number in that's less than or equal to 7. If I put a 7 in there, it's true. Okay, if I put a negative 19.265, it's true. Any number less than or equal to 7. So that's why we have a solid dot. What kind of dot do we have if we're not equal to 7? Open. So if it said X less than 7, you would put an open circle at 7. Then you would still put a nice big fat arrow all the way to the left. Okay. Okay. So now we're going to take a look at a new notation called interval notation. So the interval that represents this number line up here looks like this. Okay? And let me explain what this means. When you have an interval, whatever your smaller quantity is always the first thing that goes here. So negative infinity is the smallest number here, or the smallest concept, the smallest quantity. We can't include negative infinity because it's not a number, so we use an open parenthesis. So this says the same thing as saying all x's, the set of all x, this is our set builder notation, the set of all x such that x is less than or equal to 7. This is how we would have to write this in set builder notation. And we want to now just shortcut it a little bit. So 7 is the largest number it can be. And since 7's included, notice, doesn't this look like a staple? Doesn't this bracket have the same shape as a staple? So you're stapling that number into your set. It's being included. So that's where we use a bracket. And then we say it starts at 7, and then it goes all the way to the left to be negative infinity. And that has to have an open parenthesis. All right? So this is a new notation. We're going to have some practice with it now. So let's see. If we had this notation, what numbers would be in that solution set as it now appears? Let's try to do it on the number line first. So what does this represent on our number line, our real number line? Anybody want to help me? Solid dots or open dots? Would I put solid dots or open dots? Solid, because both numbers have a staple, right? So they're saying, I'm going to staple 2 on my number line. There it is. Staple the 2 and staple the 3. And it's everything in between those two. And there's an infinite, that's an infinite solution set because there's an infinite number of numbers just between 2 and 3. Okay. So the square brackets indicate that the endpoints 2 and 3 are included in your solution set. Again, this is how we'd have to write this thing in set builder notation. Yuck, it's a lot of work when I can just write 2, 3 with little brackets on it, right? So this is like a handy dandy quick notation, very efficient. Okay, the next example here is an example of an open interval. We call this a closed interval. And it's the same as this. It's the set of every single number in the world that's less than 5 and bigger than -1. Okay, so because I don't have any staples on there, I put an open circle at -1 and an open circle at 5, and then I shade everything in, whoops, everything in between without moving my monitor. Okay, so that represents every single number that's less than 5 or greater than -1. All right. Can't be -1 or 5, right? That would not be happy here, because it says I can go as close to 5 as I can, but I'll never be 5. I can go as close to -1 as I can, but I'll never be a -1. That's not in my solution set. All right, so you try this next one at your seat. See if you can graph this. This is the interval notation. This is a set builder notation. Try graphing that. Okay. Jasmine, how'd we do this one? How'd you do it? Solid dot on the 1, and what gave you that idea? Right? Well, it's not a closed interval. It just has that little bracket, right, that says to include it, yeah? The staple. The -4 has open because it's a parenthesis, and then what? Fill in everything in between, right? All right, any questions on that? No, no arrow, because it's bounded. If I were going out in either direction like this, Kieran, if I had something like this, that's a good question, because if you had something like this and something like this, okay, I would need the union of two intervals to represent that. I would say this is -∞, comma, -4, like that, because I'm not including the -4, and I always have to use parentheses when I'm talking about positive or negative infinity. That's one part of my solution set. I got another whole infinite solution set to the right of that that includes 5 and goes all the way. So then you would go union like that. You'd put a parenthesis 5, comma, and then what do I put after the 5? It's going all the way to the right. Infinity, parenthesis, right. So you only use arrows, Karen, when you're going off to infinity on either side. So sometimes your solution set would look like this. And you have to use that union symbol. Okay, notice it's like a U, but it doesn't have a stem on it. A lot of people do like a U. I see this a lot on students' papers. They go like that. That's not the union symbol. This is, I wouldn't take off of that. I just wanted to mention it. Okay. All right. So let's take a look. Why do we need this notation? Because when we solve an inequality, a linear inequality, we don't get one answer, we don't get two answers, we get a whole infinite solution set, and we have to have a way of representing it. We now have 3 ways to do it: a number line, set builder notation, and an interval notation. Interval notation, once you get it, is really key. So does anybody remember how we solve linear inequalities? Yeah, Bree? So you approach it just as if it were an equation, right, by subtracting 3. So she's saying, I need to still solve for x. I'm just going to subtract 3 from both sides. Okay, Bree, what would that leave me with? -3. Yep, let me, oops, I don't want to paint anything. Let me just make that so I can read it. Okay, you can read it. Okay, it's greater than or equal to -3, and then what would you do? Divide by 3. Okay, so we have a little controversy. Is it when we divide by anything? And Sharimar says, is it just when we divide by negative? Well, how are we going to know? We can, why would we divide by negative when the coefficient is 3? If it was negative 3x, we'd have to divide by negative 3, right, to make positive 1. So how do we investigate this? We've got two different answers. I could tell you, or well, let's try it both ways. So one way, we don't know yet. We don't know, and this is how you can figure it out for yourself. So Bree thinks, but she's not sure, that maybe you have to flip the inequality. You have to change its direction. So one idea is I'd get an x on this side, I'd get a negative 1 on this side, and here's the question: does that become less than or equal to negative 1? That's one question. There's another school of thought that says, nope, because I'm dividing by a positive number, I keep everything the same. So how do we know? Well, if this is the solution, if x is supposed to be less than or equal to negative 1, let's pick a number less than negative 1 and throw it back in and see what we get. So give me a nice number that's less than negative 1. Negative 2. All right. So I'm going to go back and try negative 2. 3 times negative 2 plus 3, is that greater than or equal to 0? Let's see. Negative 6 plus 3, is that greater than or equal to 0? Negative 3, is that greater than or equal to 0? No. So it's not any time you divide. Well, let's still check out the other one. How about x greater than or equal to negative 1? Give me a nice number greater than negative 1. Even nicer. That's easier to work. 0, that's really easy to work with. All right, that's really easy. Is 3 greater than or equal to 0? Okay, so it's not when you divide. It's when you divide by a very particular type of number, which is when you divide or multiply, since those are inverse operations, by a negative number. That's the only time solving an inequality is different. So we've decided it's not that route. We've decided x has to be greater than or equal to negative 1. And because it has an equal sign in there, we're going to put a solid dot. If we were graphing this on the number line, we would do this. If we were using set builder notation, we put our little curly braces x such that x is greater than negative 1, and you literally just write your solution, your inequality in there. And if we're using interval notation, someone tell me what to write, because I keep forgetting what to do. How would I represent that solution set just with interval notation? Take a risk, take a chance. Go ahead. The square one, the bracket, the staple, yep. Negative 1, because that's the very smallest number in the solution set. But I need one other little thing before I put comma, infinity, and then how do I close it off? With a parenthesis. Yep, there you go. All right, so we just said if we multiply or divide both sides by a negative number, we've got to reverse the direction. So what are we going to do in B to solve B here? Divide both sides by negative 4. You get x here, you get negative 2 here, and what's the change? Your inequality reverses direction, right? So instead of it being less than, it's going to be greater than. You can always check yourself by throwing, if you, just to make sure you've got it in the right direction. If I take a number bigger than negative 2, let's take 10. Negative 4 times 10 is negative 40. That's definitely less than 8. So on the number line, I have an open circle at negative 2, and I shade everything to the right. Set builder notation, braces, curly braces. It's the set of all x such that x is greater than negative 2. You literally just write your inequality right in there on the right-hand side. And then interval notation. Kai, can you help me with that? Negative 2, yeah. 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 And what? Parentheses on both. Perfect. Okay. So that's how you deal with a linear inequality. Right? So now I think you have some exercises that I'm going to ask you to work on together. I'm not going to do the fractions. You can read about that in your book and homework. So, oh boy, never mind. I can't do that to you because we still got these other ones to do. All right. Sorry, we're not going to get to the exercise today. But look at this. Which of these would you prefer to solve? The second one. Why? No fractions. And remember what we talked about when we had equations with constants in the denominator? Get rid of them. Yuck. Ugly fractions. And you do that by multiplying everything on both sides by a multiple, preferably the smallest multiple. In this case would be 6. So we're going to multiply both sides of the inequality, everything on both sides, multiply everything on both sides of the inequality by 6. So here's my original inequality. I always put any numerator or denominator that has more than one term in parentheses. So that's the first thing I always do. And now I'm going to bop each one by the number 6. And since I'm doing the same thing to both sides of the equation, I'm not breaking any laws of algebra or arithmetic. Right? So I'm multiplying both sides of the equation by 6. And that's a very lovely number because each one of these denominators is a factor of 6, so I can reduce it. And now I get 3 times x minus 4 on the left side. My inequality is greater than or equal to. My 3 cancels into 6 twice here, and I get 2 times x minus 2. My 6's cancel here, and I get 5 times 1, which is 5. And from there, it's a piece of cake because it's just a linear inequality with no fractions. Right? So you say to yourself, well, what if I get a negative x? Well, you can control this sometimes. You couldn't control it with the last problem we did, negative 4x equals 8, because there was nothing you could do. Well, there actually was, but we'll just stick with this one. So let's solve this. I would use the distributive property on the left-hand side, distributive property on the right-hand side. I combine like terms. There aren't any on the left-hand side. Combine like terms on the right side, and I get this. So now it's totally up to you. You have x terms on both sides of your equation. If you decide to subtract 3x from the left-hand side and the right-hand side, you're setting yourself up to have a negative coefficient for x, which means you have to remember that darn rule. If you subtract 2x from both sides, you're golden because it will give you positive 1x, and you don't have to worry about the rule. So make life easy for yourself. Always bring your x's to this. When you have x terms on both sides of inequality, keep the coefficient positive. Then you don't have to remember anything. It just looks like a regular old equation. So here I'm going to add 12 to both sides and subtract 2x from both sides. I'm going to do it all in one fell swoop. I see that on your papers a lot of time, right? We don't want to take the time to. So I get 1x on this side, and I get 13 on that side, and I'm done. I don't have to worry about any sign changes. So if I represent this solution set with inequalities, it begins at 13 with a staple, my bracket, and it goes all the way out to positive infinity with a parenthesis. Okay. So let's do this in steps then. So first I'm going to add 12 to both sides, Joseph, okay? Add 12 to both sides. And I get 3x is greater than or equal to 2x plus 13. And now I want to get all my x's on one side, so I subtract 2x. And I get x is greater than or equal to 13.
Yeah, I got it now.
Okay. All right. So Friday, I will start with this. On Friday, if you may have 1 or 2 of these for homework so you can read it. Or you know what? I'll tell you what I'll do. Right after you leave, Okay, to solve a compound inequality, there's a couple of approaches. The compound inequality would have started off looking like this. And one way to solve this is to break it into two separate inequalities where you start with the middle and you say x minus 4 is greater than negative 6 and x minus 4 is greater than or equal to, less than or equal to 1. And then you solve this inequality by adding 4 to both sides, and you get x is greater than negative 2, and you add 4 to both sides here, and you get x is less than or equal to 5. So that represents two different solution sets. So let's use interval notation to represent this. X is greater than negative 2. So that means we have a parenthesis with negative 2, comma, infinity. Here this says x is less than 5, less than or equal to 5. So that means that 5 is our biggest number in this solution set to negative infinity.